Hello everyone, I present to you the results of the FLOWTOM Work Package 2 on learning-based forecasting of metocean variables. I'm Marcille and I've been pursuing a PhD on this topic for the last 4 years. I'll give you a bit of context on the topic. So offshore operations are subject to environmental limitations, mainly wind speed, waves, current, but we can think about lightning, visibility. And this is a great additional cost for offshore projects with difficulties in site accessibility, causing weather downtime and eventually putting crew and material at risk. The numerical prediction models that are used to make decision making operationally are subject to some limitations in their estimation of the uncertainties and how close to real time they can assimilate measurements data from local weather stations. And we are working at sites with very low data availability. So the development of learning-based forecast models in this context opens new ways of doing forecasting for metocean variables, and this is what we're going to explore in this work. So the objectives of this work are twofold. The first one is to explore how we can, with learning-based metocean forecasting, improve the operations at sea. So we constructed a metocean dataset in the French Mediterranean Sea that is representative of floating offshore wind development site to develop the methodology. We explored learning-based models for the multivariate probabilistic forecasting of metocean variables, and this gave birth to an article in 2024, and we proposed a framework for weather window forecasting. The second question is, what does this imply in terms of in-situ measurements, standards evolution, and forecast evaluation? So for this topic, we developed a data-driven methodology for the siting of offshore wind measurements campaigns. And this will not be described in this webinar, but you can find information in the article from Marcille et al. In 2023. And we proposed an evaluation framework dedicated to offshore operations. So I'm going to present you the results from the article in 2024 about deep learning for short-term probabilistic forecast of metocean variables. The experimental setup that we worked on is basically taking as input numerical predictions around a certain target offshore from numerical models of weather and wave for the next 24 hours in the future, recent measurements from neighboring in-situ measurement stations, from weather stations and wave buoy in the past for the last 24 hours, put that into a big deep learning model to predict the conditions at site for the next 24 hours in a multivariate probabilistic framework. We constructed two datasets to study the methodology. The first one is based on an open source dataset by Météo France, METEONET, that was published in 2020, and is using the Porquerolles weather station as the target. It's only focusing on the wind forecasting. It lasts 3 years and has only 6 hours forecast in the future. The second one, which is more complete, uses measurement campaigns on the Plany Island offshore Marseille, a LiDAR campaign with wind measurements up to hub height, collocated with a wave buoy at the Plany Island for 2 years and in a 24 hours ahead forecast framework. So those two datasets have in common that they use numerical simulated data in the future as a physical proxy of the future situation. Measurement data from neighboring measurements as the best guess from the current situation, current state of the system, to reproduce a target data offshore that is unobserved. We propose an architecture to map between numerical weather prediction, neighboring in-situ data, and the target station measurements. We used a convolutional encoding to extract the data from the input, the two-dimensional convolutional neural network for the specialized numerical predictions, and a one-dimensional convolutional neural network for the temporal in-situ measurements. Using those two convolutional neural networks, we project the data into a latent space to which we concatenate the prediction at the closest grid point. We use a multi-layer perceptron to predict the parameters of a probability distribution per time step. So we make the assumption that each time step is described by a Gaussian distribution of the forecasted variables. We also studied an added block to transform the Gaussian distribution into a distribution that is more complex, and we use for that a generative deep learning approach called normalizing flows. And doing so, we relax the assumption on the shape of the posterior distribution. We obtain a time series of multivariate probability distribution in the variable space, and we compare these probability distributions with the observation by computing the likelihood of the observations given the probability distributions. The whole architecture is trained to minimize this loss function, so the likelihood of the observations. We called thereafter this model convolutional encoding for short-term forecasting, so conv-ESTF. We compare the results obtained with these models with several benchmark models, the first one being the numerical prediction at the closest grid point that we corrected on the training dataset with ordinary least squares, and that we augmented to a probabilistic forecast by computing an empirical covariance on the training dataset. The second benchmark is using analog stochastic, which was proposed by Lorentz in 1969, and it uses past trajectories from similar weather situations to estimate the evolution of the state of the system. We finally implemented a multi-nonlinear regression framework using gradient boosting machines that was applied to a similar problem by Gilbert et al. In 2019. So we compared those three models with the conv-STF with the Gaussian output and the conv-STF NF transformed with normalizing flows. Some results on the forecast quality. We see on this graph, compared to the dashed blue line from the numerical weather prediction output, that all the proposed models significantly improve the forecasting in terms of root mean square error. There is an important forecast improvement, and this shows the importance of post-processing numerical weather predictions at sea. We see also that the large data processing that is allowed by deep learning significantly improves the forecast. On this graph, you can see for the orange bar the results, the RMSE obtained by training the deep learning model using only numerical weather prediction as input. The green one is using numerical weather prediction and in situ data, and the gray one is using numerical weather prediction, in situ data, and the closest green point. So you can see that all these sources of data improve the forecasting. The main variability in the obtained errors is due to data representativity. Since we are working with only 3 years of data, the split between training, testing, and validation dataset is implying some differences in the data that we treat. So we cannot guarantee that the data that we have in the training dataset is representative of the underlying distribution of the data. Longer datasets improve the forecast quality and reduces the variability. So this should advocate for longer and larger measurement campaign at sea. Now, to evaluate the probabilistic results of the forecast, we need a special forecast evaluation framework. We will compare the sharpness of the distribution, so the concentration of observation in the distribution, and the calibration of the distribution. So the calibration is the statistical consistency of the distribution. You have on this graph the rank histograms that are plotting where in the distribution we find the observations, and a perfect rank histogram would be flat with 10% of the observation in each decile of the distribution. You can see on this graph that the conv-STF with normalizing flows is significantly improving the reliability of the forecasts, and you can see with the probabilistic metrics in the table that we have a significant improvement compared to the numerical model with the empirical covariance embedding, especially in a variogram score, which describes the correlation structure between the variables. In this case, we're talking about forecasting wind and wave jointly on the Planier dataset, and the importance of the correlation structure highlights the difficult and complex relationship between the wind variables and the wave variables. So it is really important to treat those variables jointly in a probabilistic framework. And the fact that we gain reliability with normalizing flow is probably due to the fact that the underlying distribution is actually not Gaussian, and since normalizing flow can approximate complex distribution, then this ends up in a gain in probabilistic metrics. And you can see on this graph an example of how complex a distribution can be predicted by normalizing flows. You have a Gaussian prediction on the right and a normalizing flow prediction on the left for the wind speed in the polar plot. And on the left one, you can see discretized direction for wind speed, and this is an actual feature of the dataset, since the target that we use is an anemometer with discretized direction. And this was predicted by the network in a completely unsupervised manner. So it means that it understood the complex distribution that was in the target measurements, and it was actually able to reproduce it. So we can approximate complex distribution, and this can be very important for wind and wave joint forecasting. Some key results on those two data sets. There is a great importance of post-processing numerical weather prediction at sea, and deep learning is quite good as that, for that, because it can take as input a large amount of data without explicit pre-processing. And so this is a real advantage of deep learning methods. In terms of probabilistic forecasting, the posterior assumption must be chosen carefully, and the fact that we use normalizing flows can be a great tool to eliminate any assumption on the shape of the posterior distribution. Now we need to bear in mind that the length of the dataset is a real limitation of these studies, and it should be maximized. However, we can still have a skillful post-processing with a relatively low amount of data. So now that we have a skillful probabilistic multivariate method, we need to go to the prediction of weather windows to be able to apply that for operational decision making. From probabilistic multivariate forecast to weather window forecasting, there is some steps to take. You have here the prediction in blue of the evolution of the wave height compared to the observation in orange, and you can see dashed black line that corresponds to the operational limitation of the operation. So a weather window is defined as a situation where the environmental conditions are under limit for the duration of the operation. So in this case, you have the observed weather window at the bottom. So if the observed curve in orange is below limit for the duration of the operation, then it means that the environmental conditions are suitable for the operation. And the top line is the predicted weather window probability, and in this case we have to estimate the probability of a weather window to make the decision making whether or not to perform the operation. On the other hand, if the predicted or the observed conditions are above limit, then there is no weather window available. Now the operational decision making should be based on the estimation of a weather window probability from the forecasts. And this requires the embedding of a temporal relationship between time steps, and this is done using Gaussian copulas, which are a mathematical object to estimate high dimensional probability density. And you can find more information in the work from Marcille et al. In 2009. So in the end, we generate scenarios, which are the gray lines you can see on the graph, from which we were able to compute the weather window probability. We evaluate the quality of the generated scenarios with probabilistic metrics in the scenario space, so energy score as used before, and we have a 5% improvement in energy score using our Conv STF post-processing with the Gaussian copula framework. And we have an even more important improvement when we look at the mean square error of the weather window probability, which is called the BIOS score, the BS on the table there, and it's improved by 50% when we use uncertainty estimation compared to the situation when we have only the numerical prediction without the uncertainty. So this proves that the joint wind and wave scenario generation improves the weather window prediction, and it should then impact positively the operational management of maintenance operations. How do we take decisions from this weather window forecast? So whether we will go at sea if the weather window probability is above a certain probability threshold. And from there, we define situations where we go at sea if the probability of weather window is above the threshold, and a situation where we wait for another window if the probability is below a certain threshold. On the other hand, we observe an absence of weather window if the conditions are above the limits, and we observe a window if the conditions are below limits. And this defines 4 different cases. The case where we predict a weather window and there is actually a weather window, it's called a true positive. The situation where we predict an absence of weather window and there is actually no weather window, it's a true negative. The situation where we predict a weather window but actually the observed conditions are above limit, this is a false positive. And a situation where we predict no weather window and actually there was a window for operation, this is a false negative. And so those 4 cases describe all the different situations that we can have from these forecasts. Now, in Catterson et al. In 2016, it was defined an economic forecasting metric for operations where we measure the economic impact of making a decision given a certain forecast. And they pretend that the cost associated with this decision making is only depending on the false negative and the false positive. In this case, a false negative means missing an opportunity for an operation, and it implies production losses because of a failed maintenance and an additional downtime. The cost of a false positive, on the other hand, is then associated with vessel and crew mobilization costs. And now these 2 costs actually can define an optimum for the probability threshold, which is equal to the rational of the costs, and this was defined in Taylor and Jones in 2018. So it means that the asymmetry between the cost of false positive and the cost of false negative calls for a probabilistic decision making. If we take the economic value of the models that we developed, you have on the table here the economic forecast metric for the numerical deterministic model, numerical model with the empirical covariance matrix, and the conv STF with Gaussian copula. And you can see that we have a 10% improvement in economic forecasting metric, but we can also see that the single trajectory decision making only based on the numerical model is actually quite competitive. Now here's a graph that shows you how the different costs interact as function of the critical threshold. And so we vary the cost of false negative and false positive to explore the range of critical threshold, and then we plot the final EFM for the different models. And what you can see is that the further away we move from 0.5, so 0.5 would be a situation where the cost of false negative and false positive are equal. So the further away we go from this point, and the more important it becomes to take a probabilistic decision compared to the black line, which is the deterministic decision making from the numerical model. And you can also see that all the proposed models actually consistently improve the EFM, whatever the critical threshold. So the increased asymmetry between false positive and false negative imply an increased interest for probabilistic decision making. Now, this is a completely theoretical framework, and if we consider a dangerous event happening during the operation, let's say we dropped someone in the wind turbine and we are not able to lift him back, so all these dangerous events, they are associated with certain cost, C of E, and they occur as function of the observed conditions. So there's a certain probability of the dangerous event E occurring knowing the environmental conditions, so P of E knowing Y, and we introduce a risk forecasting metric, that's the economic forecasting metric, plus the risk associated with going at sea in dangerous conditions. And if we do so, we obtain the graph on the bottom. For this graph, you can see the full color bars that correspond to the situation with the P50 decision making, so making the decision on the median of making the decision with a critical threshold of 50%, and the dashed bar, they correspond to the decision making with P critical. You can see that the P critical decision making consistently improves the EFN on the left graph, while it significantly improves the risk on the right graph here. And what we can see is that the risk considerations tend to favor conservative models. But let's put it the other way. Economic optimum tends to increase the risk taken during operations. So if we try to reach this economic optimum, we would go at sea in more marginal conditions. So we advocate for a risk consideration in the model evaluation to reflect the human factor in decision making. Some takeaway messages. Deep learning for metocean forecasting is a very interesting tool. We can build skillful forecasts for post-processing using a large amount of data as input, and we can use that as an opportunity for near real-time forecasting and then for near real-time decision making. We introduced normalizing flows as a way to approximate complex posterior distributions, and we showed that this is of interest for the joint wind and wave forecasting. As for decision making under uncertainty, this is typical for offshore operations. There is a need for this joint probabilistic forecasting of all the limiting parameters, and dedicated forecast models should be developed for these applications, which are very specific. From the deep learning for metocean forecasting, we need to move to weather window forecasting for the decision making. So we introduced several techniques for scenario generation, and we proposed dedicated value metrics for their evaluations. And we also introduced the notion of risk into a state-of-the-art economic metric. So the whole framework there goes from the construction of a data set, construction of the experiment, design of the model, and then evaluation of the forecast with knowing the constraints of the offshore operations. This project actually raises very interesting research questions and research perspectives. All this work could be included in a decision-making tool for optimized offshore operations. It could be applied to other applications related to wind energy, such as power production, turbulence prediction, wind profiles, etc. It would be very interesting to compare the proposed models with ensemble predictions from numerical models and to apply that on a real maintenance sequence data. And finally, we were able to construct skillful models, but we would need larger and longer measurement campaigns for offshore wind research. Thank you very much for your attention.